Today we're diving into a piece of technology so small it's basically invisible, but it might just have the power to detect a chemical threat that's been hiding in plain sight for years. This is a story about a huge danger and a ridiculously tiny solution.
And that question you're looking at right now, it's not just some thought experiment. It points to a real-world problem. And it's exactly why scientists are pushing the absolute limits of nanotechnology to help keep us all safe.
All right, first up, let's really get a handle on the threat itself. We're talking about a chemical compound that pretty much leads a dangerous double life.
So this is chloropicrin, or CP for short. Now, on one hand, it's a tool used in agriculture to fumigate soil, but it's got a much, much darker history. It was actually used as a tear gas back in World War I, and yeah, it's classified as a chemical weapon. Exposure to it causes this nasty list of symptoms. We're talking severe irritation in your eyes and throat, chest pain, shortness of breath. You get the picture.
This stuff is no joke. It's a Category 1 toxic agent that seriously messes with your lungs and eyes. But here's the real kicker. Detecting it is incredibly difficult. We just don't have a good method that's portable, super sensitive, and fast. And that gap, well, that's a huge problem for public safety.
So how in the world do you detect something so dangerous and elusive? Well, researchers have an idea, and it involves making the detector unbelievably, almost impossibly small.
Okay, so we're talking about something called a nanotube. If you're new to this, just picture a teeny tiny, hollow tube made of atoms all rolled up into a perfect cylinder. The scale here is it's mind-blowing. We're talking so small that materials start to get entirely new and, frankly, weird properties.
And this right here, this is the hero of our story, a zinc sulfide nanotube, or ZnS. Scientists picked this specific material because it has some really unique electronic and optical properties, which makes it a fantastic candidate for a chemical sensor. Its whole structure is the key.
So, you might be asking, why bother with something so tiny? Well, it all comes down to surface area. Imagine a brick, that's your bulk material. Now, imagine taking that same brick and stretching it out into a massive, super thin sheet and then rolling it up. You'd have a gigantic surface area, right? That's the nanomaterial. All that extra space gives gas molecules way more room to interact, which makes these things incredibly sensitive.
But having a promising material is one thing. You've got to prove it actually works. So how did the researchers put this thing to the test?
I mean, think about it. You can't just pull out a microscope and watch a single molecule land on a nanotube. The whole thing happens at a scale and a speed that's pretty much impossible to see directly. So, what do?
Well, you do the next best thing. You build a virtual lab. Using some seriously heavy-duty, quantum-level calculations, scientists ran these powerful computer simulations. This let them model exactly what happens when one single molecule of chloropicrin gets close and sticks to the nanotube's surface. They even tested 4 different ways it could attach, which they just labeled A, B, C, and D.
And what they found in those simulations? Wow. It wasn't just some small tweak. It was a massive, fundamental transformation of the nanotube itself.
The second that toxic molecule makes contact, the nanotube's properties change in 2 really clear, measurable ways. It basically sends out a signal saying, hey, chloropicrin is here.
So the first superpower is electrical. The best way to think about it is that the nanotube has this big energy hurdle. It's called a band gap that electrons have to jump over to create a current. But when the chloropicrin molecule shows up and attaches, that hurdle gets way, way smaller, and that makes it much easier for electricity to start flowing. And you can literally see this happening in the data. Look at the top chart here. That's the nanotube by itself, with a really wide energy gap between the bands. But now look at the charts below, after the CP attaches. See how much that gap has narrowed? That's the hurdle shrinking right before our eyes.
And we're not talking about a small drop here. In the best case scenario, the band gap shrinks by up to 40%. That is not a subtle change. That's a massive electrical signal that would be super easy to detect. It's like turning a very dim light into a searchlight.
And that's not all. The second superpower is optical. You see, a normal zinc sulfide nanotube is mostly interested in absorbing invisible ultraviolet light. But when chloropicrin latches on, it's like its tastes in light completely change. It suddenly starts absorbing light in the visible spectrum, the light that we can actually see.
This chart shows it perfectly. The top graph, that's the original nanotube. Its absorption peak is way over in the invisible UV range. But check out the graphs below, after CP shows up. That peak shifts dramatically over to the right into the visible light spectrum. Scientists call this a redshift, and it's another unmistakable signal. It's the nanotube basically changing color.
Okay, so we've got two super strong signals. The sensor is clearly very sensitive. That's awesome. But for any sensor to be truly useful in the real world, there's another really important question. Can you use it more than once?
I mean, think about it. What good is a smoke detector that only goes off once and then you have to throw it away? For a real-world device, you need it to reset itself, and you need it to do it fast. This is what's known as the recovery time.
So let's see how our little nanotube stacks up against the competition. This table compares its recovery time to some other advanced materials. And just look at these numbers. Some take seconds. One of them, a silicon carbide material, would take, well, longer than the entire age of the universe to reset. So, not exactly practical. But our ZnS Nanotube, it's in a class all by itself.
3.5 microseconds. That is ridiculously fast. A microsecond is a millionth of a second. It means this sensor can detect the molecule and then reset itself almost instantly, ready to go again. And that is the key to creating a device that gives you continuous real-time monitoring.
So let's put it all together. What do we got? We've got a sensor that's super sensitive, it's insanely fast, and it's reusable. That is the perfect trifecta for a practical device. This is the kind of thing that could be used by first responders, in factories, or for protecting the environment, and ultimately, it has the potential to save lives.
Which leaves us with a final, pretty incredible thought. We're talking about technology that makes the invisible visible. As these tiny sensors get better and better, you have to wonder, are we getting closer to a future where dangerous chemicals have absolutely nowhere left to hide?